Okay, so let's take a look at some more ways we can learn about probability through examples. All we're doing really is setting up fractions where the probability of, we're determining probability by putting the number of ways the event we're interested in can happen in the numerator and the number of total things that can happen in the denominator. Okay, there are 12 men on the basketball team. 2 are centers, 5 are guards, and the rest are forwards. So let's start taking a look at this information. I like to highlight. So we've got 2 centers, 5 guards, the rest are forwards, slight typo there. Now, they say there are 12 men on the basketball team. That's going to be our sample space. So I already know that that's going to be my denominator. Meanwhile, back to the question. What is the probability as a percent that out of 2 players chosen at random, they would be a guard and a forward? Okay, we have 2 things going on here. Now, you're pulling 2 players out. That is 2 experiments in terms of probability. Some of this can be a little bit hard to see, but first, you are going to pull out a guard. So the probability of that is, well, there are 5 guards out of 12 players. Then you're going to pull out a forward. What's the probability of that? Well, let's see these numbers. Okay, there's 12 total, 2 centers, 5 guards, that takes 7. That leaves 5 forwards, okay? So there's 5 ways to pull a forward out. Now, here's what's a little bit different. You've already pulled a guard out of the 12. He's pulled out. There are no longer 12 of your players sitting on the bench. You've asked the guard to step forward. Now you're calculating the probability that you're going to pull the forward out of the remaining 11. This denominator changes when your situation changes. Okay, these are 2 separate experiments. The first one is what is the probability of getting one of the 5 guards out of the original 12. Then it's the probability of getting one of the 5 forwards out of the remaining 11. So the probability of getting a guard and a forward in 2 tries is 5 out of 12 times 5 out of 11, or 25 out of 132. Now, good question here might be, how do we know we pulled them out in this order? Remember, the whole point was players chosen at random. What's the probability of these 2 happening to be the guard and the forward? It doesn't say first you go for a guard, then you go for a forward. When you get to more complicated counting examples, sometimes the order in which you count things matter. We're going to stay away from that for now. This is a fairly simple probability course. So we're going to look at the alternative. If instead the first person you pulled out happened to be forward, you grab one of the 12 guys at random, there are 5 forwards in there out of 12. Then we find the probability that the next time you pick one of your players at random, you're going to get a guard. 2 separate events. Pointing to one of them and saying, come here, pointing to the other one saying, come here, 2 separate experiments. So the guard's probability is now, out of the 5 guards in the remaining 11 players, the 5 out of 11 probability of pulling out the guard. So now the probability of getting a forward and then a guard, 2 separate experiments, we multiply the probabilities. It is 5 over 12 times 5 over 11. When multiplying fractions, we multiply the numerators, multiply the denominators, it's the same thing. Okay? Good way to check if you're in a situation to be sure whether the order matters or not is switch the order. If you get the same answer, it's a nice little way to double check that you've probably done it right. So if the order doesn't matter in terms of random events like this when you multiply probabilities, it'll still work out fine. You'll get the same answer in the end, either way. Okay, so this was 2 experiments. What was the probability of both experiments going a certain way? 25 out of 132 is our answer. Oh, not quite done. Problem said to figure this out as a percent. To find a percent, you take your fraction, multiply it times 100, and we get there's an 18.94% when we round. 39, round that up to 4. So there is an 18.94% chance. Either way, we figure this out. Okay, let's take a look at another one. That writing might be a little small. Let's make it bigger. You flip a coin and then roll a fair 6-sided die. Fair just means any of the sides can come up equal opportunity, equal chance. There's a 1 out of 6 chance of any of the sides coming up. Unfair would be as if you somehow weighted the die so that a certain number occurred more often as you rolled it. Flip a coin, then roll a fair 6-sided die. The coin lands heads up and the die shows an even number. We're going to find the probability of this event happening. We have 2 things. We have 2 experiments, okay? First experiment is you flip a coin. Well, the probability of the coin landing heads up, well, let's see. You flip a coin, there are 2 things that can happen. Your sample space is just heads or tails. One of those things is heads. That's the probability of your coin flipping heads. The probability of the die showing an even number. Talked about this once before. There are 6 things that can happen when you roll a die. 3 of those things involve even numbers. 3 over 6 simplifies to 1/2. These are 2 separate experiments. The probability of both is what happens when you multiply 1/2 times 1/2. The probability of the coin coming up heads multiplied by the probability of the die coming up even. You multiply these 2 fractions together, multiply your numerators, multiply your denominators, your final answer is 1/4. That is your probability of both of these things happening. 1 out of 4 times that should happen. Okay. These slides will be a PDF on my website if you want to look at them. If you prefer to look at them after we talk about them here. Okay, you roll a fair 6-sided die twice. The first roll shows a 5. The second roll shows a 6. What's the probability of this happening? Well, the probability of a 5 is 1 out of 6. There's 1 5 on your 6-sided die. There's 6 numbers that could possibly have come up. The probability of a 6, well, there's 1 way that a 6 can come up. There's 6 things that can happen. The probability of both is what happens when you multiply these 2 things. Okay? Probability of both is what happens when you multiply these 2 things. Let's go on. There are 8 shirts in your closet. There are 8 shirts in your closet. That number will come up. Again, there are 4 blue and 4 green. You randomly select one to wear on Monday and a different one on Tuesday. You wear blue shirts both days. So the question is, what is the probability of this happening? Okay, once again, these are 2 different experiments, so we'll be multiplying the separate probabilities. I'm also going to make an assumption about this problem that you don't wash the shirt Monday night and put it back. You don't have a laundry turnaround time that quick. You don't waste the water of doing the laundry that often with just 1 shirt. So the probability of the first shirt being blue, well, you got 8 items in your sample space. Your sample space of the shirts in your closet. the event of choosing a blue shirt can happen 4 different ways. Number of ways the event can happen divided by the number of elements in your sample space. 4/8 reduces to 1/2. The probability of blue again, assuming you didn't wash that one shirt and toss it back into your closet, well, your sample space is now just 7 shirts. One of them's in your laundry basket, it's no longer in your closet. The ways your event can happen is now 3. You had 4 blue shirts, you wore one. So the probability of blue on the first day is 4 out of 8. The probability of blue on the second day is 3 out of 7. The one blue shirt is removed from both the numerator and the denominator. What is the actual probability we're looking for of both of these things happening? It is, I'll use the reduced fraction, it is 1/2 the probability of the first event happening times 3/7 the probability of the second event happening. You have a 3/14 probability of winding up wearing blue shirts 2 days in a row. Okay? 2 separate experiments, multiply to find the probabilities. A basket contains 5 apples and 7 peaches. You randomly select one piece of fruit and eat it. Then you randomly select another piece of fruit. The first piece of fruit is an apple and the second is a peach. Looking at 5 apples, 7 peaches. So first, the probability that the first piece of fruit is an apple is 5 out of 12. Where did that 12 come from? Again, our total sample space is the 5 apples plus the 7 peaches. The event we're concerned about is eating an apple. There's only 5 ways to do that. That's 5/12. The probability of eating a peach having already eaten an apple. Well, there's still 7 peaches in the basket if this first event happens. So I might not have mentioned before. If you're looking at the probability of 2 events happening, to get the right answer mathematically, you have to assume that the first event did go down the way you're looking for it to. Okay? If this wasn't a peach to begin with, there's no point in going on, but we're not interested in that. We're interested in the probability of these 2 events happening. And to do that, we have to count them as if we could make them happen that way, as if we could pick. Can't in real life, but to find the probability, you have to count as if you could pick what would happen. There are 5 ways to have an apple be the first piece of fruit you pick. There's 12 pieces of fruit in there. After you've eaten the apple, we're pretending we're in control, so we can say that happened. There are 7 peaches left. Still, but there are only 11 pieces of fruit in the basket. You ate one of the apples. So now, the probability of getting a peach, assuming that the apple got eaten, is 7 out of 11. Okay, there's 7 peaches, there's only 11 pieces of fruit left, you ate the apple. So the probability of both of these things happening is the probability that you did indeed pick an apple on the first try, multiplied by the probability that you then go for the peach, apple already having been eaten. Yes, if we switch the order, we will still get the same answer of 35 over 132. That is the fractional probability that you will get an apple and a peach if you eat your fruit at random. Last one for this set. Beth and Shayna each purchase 1 raffle ticket. If a total of 11 raffle tickets are sold, that actually sounds like a very small raffle, not a very successful one if that happens, but still. If a total of 11 raffle tickets are sold and 2 winners will be selected, what is the probability that both Beth and Shayna win? Again, you have to treat this as 2 separate experiments. So the probability that they'll both win is that, first it's the probability of Beth winning. There's only one way for Beth to win. There are 11 tickets. There's 11 names in a hat, let's pretend. One of them has Beth's name on it. There's only one way to make that happen. If that happens, the probability of Shayna winning, well, there's only one way Shayna can win, but now there's only 10 tickets in the hat. So the probability of both is the 1 out of 11 probability of Beth winning multiplied by the 1 out of 10 probability of Shayna winning. It's a 1 out of 110 chance for both of them to win. Okay? You have to be careful how you write these things. There's a common misconception. I don't want to confuse you, so I'm going to try and say this carefully. I'm going to write in green what not to do. A common mistake would be saying, well, isn't there a 2 out of 11 chance that they'll both win? I mean, there's 2 of them, 2 winners. Can't we just put 2 winners into our event and the 11 raffle tickets in our sample space? Unfortunately, it doesn't work that way. This says a different thing. This conveys different information in sort of the language of probability. This says the probability of something happening, this gives us twice the probability that we want for the first event. This doesn't necessarily include our winners, okay? This is the probability, in the language of probability, this means, let's say if Beth bought 2 tickets, this would be the probability that just she wins. Okay, so that's a little bit of a different idea to convey than the probability of one event and then of another event. Okay, these are also 2 separate prizes going on here. This could be the probability of Beth winning 1 prize if the raffle only had 1 prize. You gotta be kind of careful how you frame it, and you gotta treat each separate experiment as a separate probability and multiply if you want both to happen. These are 2 separate things, Beth winning and Shayna winning, okay? This is one person having twice the probability of winning. It's not how we want to express it, okay? I hope that wasn't too confusing, and we'll do a couple of more examples of some more complicated ways to count probability in the next video.